Thank you very much. So first of all, this is a very official appointment. I thank Francesco for the hospitality, for the invitation, and I'm very happy to be here in Cisterna di Latina. And we have already discussed a lot of subjects, and today you will get a completely different story. But I think I can explain you something which might be useful for you. The topic is a geometric derivation of the Hencky strain tensor. Derivation of Henky's strain tensor. So, in doing so, I have to explain to you what is a strain, what is a strain measure, what are there as strain measures, and what is a Hencky strain measure, and what is a new kind of motivation or geometric motivation which I wanted to do. So the first thing is a strain. What should a strain be? Well, we have a domain omega in R3 for definiteness, and we have a map phi mapping the domain to some actual configuration. We have a gradient of phi, which is the deformation gradient, a 3x3 matrix or a second order tensor, and somehow we want to measure how much is phi differing from a rigid movement. So a rigid movement would be a movement where you just take your reference configuration, let's give it here a ref, you just move your body rigidly in space, translation and rotation. So a rigid movement would be characterized by phi rigid as a function of x is a rotation applied to x plus a translation, rotation and translation, and x is, small x is a point in the reference configuration. Certainly if you're just moving your object, there's no strain. Nothing happens to the object apart from this movement. And the energy which you would like to ascribe to a certain deformation state should have to do something with the strain the material endures. But now I'm making the story the other way around. The strain is a measure of deviation of the actual phi towards any rigid movement. So strain is a definition now, deviation of phi from rigid movement. In the following, we can dispose of the translational movement if you just translate the body, because from the assumption of a simple material we know that the energy should only depend on the gradient of phi. So a constant translation is immediately killed, doesn't matter. We can consider only a rotation. But how should we now measure this? It's not so simple to say that, well, some measure of phi minus q times x. Yeah? You want to measure this distance. But there is the point, we can take the gradient of phi and ask ourselves, what is the distance of the gradient of phi locally in each point to a rotation, q. The q's are in SO3, so this is my shorthand notation for orthogonal matrices. And the distance, the measure for this distance, I take the Euclidean distance. The Euclidean distance, this is a 3×3 matrix, this is a 3×3 matrix. I calculate this as being gradient phi of x minus q, and the distance on matrices is the Frobenius norm. The Frobenius matrix norm, which means you take all entries of x squared, and that's it. So this is a distance measure. You measure the gradient against the rotation. The result is some number, but perhaps you haven't taken the good rotation. There is another rotation which is closer to the gradient in one point. So I would like to have the closest q in that measure to gradient phi of x, because gradient phi is not rigid. It's not quite clear immediately which rotation you should have to take. So what we are basically interested in is not the distance of gradient phi to one rotation, but the distance to the group of rotations, the minimizer of the q's, which is the nearest rotation. Find the nearest rotation, and for this we can now say that this is the distance squared, sorry, here this should be a squared because I have a square here, the distance squared of gradient phi to SO3, meaning that I should find SO3 is a compact manifold. I should take the minimum over all rotations of this individual measure. Distance squared gradient phi q. Okay, and what do we see? If this distance here, this measure, is 0, that means your gradient phi is a rotation in every point. Because 0 means this expression is 0 over whatever the space point x is. So gradient phi of x is a rotation if this is 0 everywhere. What does it mean? This is the first consequence.
You are fixing the point x.
Now I'm okay. Now I'm considering this, and I'm not looking at one point x, but simultaneously over the whole body. If I know that the distance of gradient phi of x q SO3 is equal to 0 for all x in omega, which doesn't tell you which rotation you have to take. In each point you could have another rotation making the distance 0. You don't know yet. But we will see in a moment that the situation is much simpler. So if you have this, you see that the gradient phi of x is a member of SO3 for all x in omega, which means the gradient phi of x is a rotation q of x. You could again have in each space point another rotation. This is a partial differential system of first order, PDE system of first order. It's clear you have one derivative, the gradient, and here you have a rotation. What tells you this system? There is a very strong implication. This implies that the gradient of phi or at each space point x is in fact a constant rotation. There are not many rotations around, there's only one constant rotation. I will explain in a minute how this comes about. If this is the case, you can completely integrate, and you see that this is implying that phi of x is q hat x plus some translation, constant translation. How do you get from here in each space point a rotation to in each point, in each space point, the same rotation? How do you get this? You have to solve this partial differential system of equations. And what you do, there are several ways to arrive from here to here. It's a rigidity theorem. Rigidity means something is rigid. Okay, the name is speaking for itself. But there are several fields in mathematics where you have rigidity theorems. For example, in complex analysis, you have Liouville's theorem telling you a certain derivative is doing something, then it can only be constant. And this is in the same vein. The reasoning which I would like to mention is the following. We assume that phi is a smooth mapping, and that the gradient of a smooth mapping is locally a rotation. That means on that side here I can use derivatives, further derivatives. Take derivatives on both sides. Namely just those derivatives which appear by the lemma of Schwarz, the derivatives which interchange. And in doing so I can apply to the left-hand side the curl, the rotation as an operator. A rotation now has two meanings. A rotation can be an orthogonal matrix, or the rotation of a vector field, the curl of a vector field. Now the phi, the gradient phi is not a vector field, it's a matrix, but it's a matrix made up of three, not columns, the rows. So the gradient of phi is made up of the gradient of phi 1, the first component as a row, the second component as a row, the third component as a row, just my shorthand notation for this. And I define an operator which is the curl of a matrix is just to take the curl of each row. And then you see, if you take the curl of this matrix, it is the curl, let's say the small curl, on each row, and the curl of a gradient vanishes. Therefore, the curl of gradient phi is 0, regardless of the space point where you are. And we had equality. On the right hand side, you have a rotation matrix, an orthogonal matrix, so I'm allowed to write this is the curl of q of x, which is 0. The curl of a rotation orthogonal matrix is 0. What does it tell you? There is a theorem which I proved in 2008, namely the following. The curl, this curl of a rotation matrix, which depends on a space variable, and you take the Frobenius norm, the Frobenius matrix norm, no integration, it's an algebraic statement, estimates with a given constant, I can give you this constant precisely, all derivatives, all partial derivatives of q. Let's call this dx q of x. Now Q is a 3 by 3 orthogonal matrix. All partial derivatives is a third order tensor. You have 27 entries. So this should be an R27 here. R27. It's not important. It's just telling you that it controls all partial derivatives. If Q of x in SO3. Now we are back in business. The curl of my orthogonal matrix is 0. This guy is 0. This guy is 0. But this is now just all derivatives of a field are 0, means the field must be constant. Therefore, together with this, Q of x is in fact not a Q of x, but a Q hat of x. That means we have indeed this expression, and we see that this measure here, this expression being 0 tells me I'm in a rigid movement, and otherwise it's a positive expression. It measures somehow the distance of phi to being a rigid movement. What is this measure? Can we specify this measure? Having an analytic expression for this measure? Well, we have to look what it is. It is this Frobenius norm and the minimum over all Q's. And on the next blackboard I will do this calculation. I will come to it in a moment. Yeah. This is a kind of motivation, because the structure which I'm presenting here will then be generalized to a situation where you cannot go a short way, go a direct way. You have to somehow copy all these steps, distances, calculations, optimization, and so on, and then you will see that you can just follow this picture then. Okay, let's calculate the optimal rotation. Okay. So we have the distance squared gradient phi of x SO3 defined as the minimum over all Q of gradient phi of x minus Q squared in the Frobenius norm. Now this is an algebraic question. Given locally a deformation gradient, which I now abbreviate with f, and the distance to rotations. What is the best rotation at given f to make this smallest? Make this smallest with respect to Q in SO3. The answer is known. The answer is known. The Q is uniquely given. Q is uniquely given by the orthogonal factor of the polar decomposition of f. That means I am writing f in a unique way as a rotation r times, well, a stretch u. U is the square root of f transpose f, and r is then uniquely defined as f times u to the minus 1. So r is an SO3, and u is a member of positive definite symmetric matrices. The positive definiteness coming from the assumption which I have made that F is invertible. Then this is a positive definite matrix. And now, the optimal Q being this rotation, we can calculate this guy to be the minimum of F minus Q is equal to the minimum of Q transposed F minus the identity. Why is this? The F here is just still the Frobenius norm, it's not this F, because the Frobenius norm is left invariant and right invariant under rotations. Yeah, if I'm multiplying here with a rotation, it doesn't change the length. The length of a vector is invariant under rotation. So I did this, I multiplied everything from the left with Q, that is Q transposed F minus Q transposed Q. This is this. Now I'm inserting my equation above. This is in fact a Q to the minus 1, Q to the minus 1 F minus identity, and I'm inserting now the smallest Q, which is the R. The R is an F times U to the minus 1 to the minus 1, and the result is U minus 1 without minimum. This is the minimum value. And this is the BO strain tensor. And U is the stretch. And of course, if U is equal to 1, we have already all these ingredients. Just remembering, if U is the identity, that means the square root of gradient phi transpose gradient phi is the identity, which means that gradient phi must be a rotation. And again, if it's a rotation, we had our previous development, it is a rigid rotation. That means this is indeed a strain tensor in the sense that it measures the difference to a rigid movement. Okay, so we have seen how we get this strain tensor from introducing a distance measure of gradients of deformations to the group of rotations. What is special here is that, and you didn't complain, I used as distance measure here the distance which has been given by the Frobenius matrix norm on matrices. This is how I measured things. Now, the gradient of phi is the gradient of a deformation, and we are only considering deformations which are invertible, so that the gradient of phi has non-zero determinant. Let me make another simplification which will help you understand the next step. Assume your material is incompressible. From now, material is incompressible, which means that our deformation map should locally like determinant of gradient phi is equal to 1. Determinant of gradient phi of x in each point x of omega ref is equal to 1. That is, the gradient of phi is a member of a group, a special group of matrices, namely the special linear group. gradient phi of x is element of the special linear group, which is just all x in 3 by 3 matrices, such that the determinant of x is equal to 1. And this is a group. You can multiply elements and so on. Now consider our distance in terms of the Euclidean distance measure. The problem is that it does not at all respect the group structure of SL3. And there a picture should be helpful. But before doing that, let me just say a little bit more about the strain tensor. Based on this development arriving at U, you can now devise a whole family of strain measures which are not exactly like this distance, but which also do the job in controlling rigid rotations. Namely, you can say the U is a positive definite matrix. You can orthogonally diagonalize it. R transpose R a rotation, will give you a diagonal matrix, du diagonal. So you have the stretches, the lambda i's being this, the du is lambda 1, lambda 2, lambda 3. And as a measure, you have a whole family of strain measures, the so-called Hill type strain measures. Which go as following. You can take 1 over m any number, lambda I to the power m minus 1. This is a strain. And for m equals, this is for m not equal to 0, and for m equals 0, you take the logarithm of lambda I. This is okay, the lambdas must be positive. The logarithm. The only thing you want to see, and you see it immediately, is if you have a quadratic or whatever expression in these terms, making this 0 means that the lambda I must be 1. If this is 0 means the lambda I must be 1, and then you are back in that situation here, and you have a rigid rotation. So rigid rotations here are characterized by rigid if lambda I equal to 1. Okay, and for m equals 1, we get the Biot strain. For m equals 2, we would have a kind of Cauchy-Green strain. We can also have m to the minus 1. You measure somehow the inverse deformation, then it's a kind of Almanzi strain. And for m equals 0, it's the Hencky strain. Hencky strain. Now Hencky was a German mechanician and a mathematician in the first half of the century, of the last century. And he was occupied with plasticity models and civil engineering problems. And he used extensively this strain measure, because now when you want to write down a free energy for your deformation, for accounting for your deformation, you write it as a function of these variables. But you are free to choose whatever set of variables you want. And he chose this one for very peculiar reasons. Because in a one-dimensional situation, and other people before him had already considered the one-dimensional elongation of a slab and came up with this strain measure, because if you use this strain measure, you can additively work. Namely, you start straining a slab, Then you have a certain strain, and then you have another strain on top of the first strain, but the reference configuration is the already strained one. This is a kind of digression. So you start with a unit slab, you have a certain strain doing this. Now from here you can have a new strain measure, and you continue, and if you use any other strain measure than that one, these strains do not combine additively as a measure from here to the last one. Of course, I can go from the unit length always to the final straining, but the final straining would have nothing to do with the sequences which I had done before if I was using these strain measures. They're every time relative. Only if you use this strain measure, it turns out that adding up the strains in each incremental step is the same as immediately getting the full strain. I could talk a long while about this effect, which is very nice. So people considered this logarithmic strain, and then there was the famous book by Trustel and Knoll accounting for different strain measures and so on, and they said, well, listen guys, it is of no importance what strain measure you use as long as you have this kind of behavior, as long as you control something. Completely destroying, so to speak, previous authors who claimed that this strain measure has a certain advantage. Of course, this strain measure here, you can look at it in a one-dimensional situation as giving a stress-strain curve. We are plotting the stretch versus for a linear relation, of course. Let's do this and combine these families, what they predict. We do the following. We use a linear relation between the strain measure and the elongation. So I'm plotting the stretch, lambda, which is uniquely given, versus the strain measure, which is also a measure for the stress. So let's do it for m equals 1. For m equals 1, let this be here the identity. You have a linear relation, lambda minus 1. So lambda minus 1, this is this relation. If you increase lambda beyond 1, an increase, otherwise a decrease. Do it for lambda, this is for m equal 1. Then you have m equals to 2, you have lambda squared minus 1. You are getting this kind of behavior. If you have a higher derivative, a higher exponent, it's getting steeper. What you already observe is that you have a decrease of the stiffness under pressure. The m equals 1 is just treating it equal, pressure and elongation. Here you have an increase of stiffness for elongation and a decrease of stiffness in pressure. And now let's look at what the logarithm is telling us. The logarithm is doing this. M equals 0 is a logarithm. And for lambda to 0, which is of course you want to pressure it heavily, you have a singularity, which is physically nice because you cannot compress a body to 0 volume. The baseline is of course as a tangent, as linearization in the identity, all measures coincide. In the identity everything is the same. But for large deformations, the behavior of the logarithm is somehow preferable because it tells you even for ideal elasticity, under elongation you will lose stiffness, and under pressure you will have increased resistance. And I can tell you, when you make ideal experiments, people did that 100 years before, you have a steel wire, let's say 50 meters long, in a church tower, and you put some small weight on the wire, and you record the movement of the wire by the application of the small weight with a microscope. You have a precision of measuring strain which is unbelievable. 50 meters long, relative strain, and the elongation with a microscope. And so they were interested in what is the real ideal elastic behavior of such a steel wire. And then they tabulated it. And the result is quite remarkable. The precision means you are in a, let's say, nanoscale. Yeah? What do you see? What kind of behavior do you see? The answer is a logarithmic behavior. You never see, under no scale, a tangent. Well, there is a tangent. There is a tangent, but you never see just a straight line, but you see a curve. A curve just taking up the behavior of the logarithm. The curve looks like that. Of course, you are not saying something about compressing to zero or large strains. Even this is to be interpreted as a look into the neighborhood of the identity. You see this. That means also there is no material which is linear elastic. Yeah? Linear elasticity is a mathematical approximation, and you work with a tangent to that line. Okay, so there is a certain reasoning why perhaps the logarithmic strain is, for ideal elastic situations, is a good one. I mean, if I'm now stretching further, there might be plasticity, nonlinear effects which have to do with something else. We are talking about ideal elasticity. So, but Trustel and Noll, they somehow blamed all people who thought that the logarithm would be a better measure. But then there was a revived interest in the logarithmic Hencky strain, namely when doing plasticity theory. People had invented a small strain plasticity theory, which is defined in terms of additive decompositions, worked very well, and then they wanted to do it in a finite strain regime. And the logarithm has a nice property. The logarithm of a product is the sum of the logarithm. The other way around, if you have a theory where you work with sums, the linear theory, or with differences, you can just shift it to the finite regime by appropriately using the logarithm. And that's what they did, and their results were phenomenally good, because the logarithm of a matrix, of a positive definite matrix, the logarithm of u, what should that be? Well, you take the logarithm of the diagonal matrix which goes with u, and the logarithm of u is equal to the logarithm of r transposed dur. This is just an identity for u. You diagonalize r, and then the logarithm is, by its very definition, of a matrix. We are now speaking about a matrix function. The logarithm is an isotropic tensor function, that is, the rotations on the left and the right, r transpose on the left, r on the right, go out. Yeah? It's the same as r transposed the logarithm of du times r. I will show you in a moment.
Defined by Asinius, right?
Yes. I will give this in a moment. And then here you can apply the logarithm just to the singular, to the eigenvalues of du. It's just a diagonal operation with the classical logarithm. So they used this device for plasticity, and they were very successful. And again, there was a huge debate whether this Hencky strain has some inherent advantages over other formulations. And there is a school in Bochum, in Germany, members were and are still Professor Bruns, Professor Xiao, Professor Myers, who proposed several reasons why the Hencky strain, also for plasticity, is a preferred measure. But it's a debate going on, and you never should ask for a conclusive answer. There are people doing it this way, there are other people doing it the other way, and there is no compromise. What I'm doing today is to give you another derivation of the Hencky strain measure from first principles, which might make you think about what is peculiar about the Hencky strain. Okay, now the logarithm. I will speak very in detail about the logarithm, so let me define the logarithm of a matrix. The logarithm of a matrix is just the solution of a matrix equation where the exponential appears. So what is the logarithm of a number? The logarithm of z is what? E of x equals z. Is the solution x. The logarithm of z is the solution to this equation. Yeah? X is the logarithm of z. Of course, we know z must be positive because e is the exponential is only positive, so we have some restrictions for the logarithm. So, as a matrix equation, we can write this as a matrix equation. So we want to know what is the logarithm of a matrix. Well, we write the corresponding matrix equation. The exponential of a matrix is equal to the matrix Z. And the exponential, you can give it in closed form, not in closed form, in series expansion. The exponential of x is 1 plus x squared half, and so on. It's a series, and it converges. And you look for solutions.
Converges in the F norm.
In any norm. In any norm. The exponential is a series which converges in any norm. Because this is a finite dimensional thing. It's an R9. 3x3 matrices. All norms are equivalent on finite dimensional spaces. But we could consider the Euclidean norm. So this is defined, and the inverse function, the solution to the equation, is the logarithm. And for the logarithm, unfortunately or fortunately, because the calculus is like that, you cannot dispute it, you have also a series expansion of the logarithm, but only in the neighborhood of the identity. Not for any value, but in the neighborhood of the identity. You have the logarithm of z is equal to, of 1 plus y is equal to y minus y square, and there is a 1/2, and so on. A certain expansion for the logarithm. There are even many expansions for the logarithm regarding where you are. The problem is that this series is not converging unconditionally. You must be in the neighborhood of 1. So there is already a problem with the logarithm. What you can see is that the exponential function, and therefore also the logarithmic function, is an isotropic tensor function in that sense. If you, from the left and the right, multiply in that combination with an orthogonal matrix, this orthogonal matrix will go out. For the exponential, I will show this immediately so that you can see it's nothing special about it. The exponential of q transposed xq, by its series definition, it's very nice. Namely, you take the first one, 1 plus q transposed xq plus 1/2 q transposed xq bracket a square times q transposed xq and so on. So what happens? And this happens again in all these terms. This q is killed against itself, and you have a q transposed on the left and a q on the right, a q transposed on the left, a q on the right, and you can write this as q transposed 1 plus x square half plus q. And the series still converges, nothing has changed. That means this guy is equal to, this is the exponential of x, this guy is equal to q transposed x times q. And these are all matrix operations, matrix multiplications. And I'm not doing it, the calculation, you can immediately see that for the solution x of this equation, there must be the same kind of combination. If you change x by q transposed xq, that means you get the q's outside and they will be on the left hand, on the right hand side for that, and that must imply some relations for the logarithm. And in fact, the logarithm is also an isotropic tensor function. We call this behavior here an isotropic tensor function. Isotropic tensor function. Okay. We have a matrix logarithm, we have a matrix exponential, and still another preparation. The problem is that not every matrix has a logarithm in real numbers. Yeah? You can take a logarithm of a positive number and the result is unique. But what about the logarithm of -1? It's not defined in terms of real numbers. But they are the complex numbers. And we could look at the equation, at this equation for z and x in complex numbers. And there we have the complex logarithm, and this is a very tricky guy because it is in a sense multi-valued because of the rotation of the unit circle. And then of course you can look at the branch cuts, thinking back of your analysis classes or whatever. You have a multi-valued logarithm. The solution to the equation, there are several. No bound about the solution, you can rotate, and then you can choose just a certain part of the branches, but this will make your logarithm not continuous. So the complex logarithm is really beastly. We are not considering the logarithm of a number, we are considering the logarithm of a matrix, which even further complicates the thing. This problem has not appeared to people before and does not appear in the strain measure of the Hencky sort because you only apply the logarithm to a positive definite matrix, which is as much as saying that you take the classical logarithm. Okay, so the matrix logarithm is a complicated object. How does it appear now in a new motivation? Back to our group structure, I said I wanted the deformation to be incompressible. I mean, the material is incompressible. And in incompressibility, we have this group of SL3, and we are still, or I am still looking at my plan, namely I want to measure distances of gradient phi, 2 rotations, but now respecting the group structure of SL3. Why this? SL3 again is a group, and I tried to draw a picture. The picture is, this is SL3. All elements here, the constraint is the determinant is equal to 1. Of course, these are 3 by 3 matrices which are embedded in all 3 by 3 matrices. And on all 3 by 3 matrices I can measure Euclidean distances. I can do this. My picture is still not complete. Imagine this is the surface of the Earth. So the surface of the Earth. And all elements on the surface should represent SL3. I haven't found a better picture. Now you want to measure the distance between 2 points on SL3 from Australia to Rome. Of course you can say that, let's go the straight line. Let's go the straight line, dig a hole, and from Australia to Rome via the straight line, the shortest distance. But then, on that straight line, you have clearly quit SL3. You are not on the surface. So, respecting the group structure of SL3 would mean that you should somehow find the shortest way on the surface from Australia to Rome. In the Euclidean case, we just took two objects, let's say x and y, being 3 by 3 matrices, and calculated the distance between them by saying that, well, the distance is take the straight line and calculate the length of the straight line. And this is indeed the distance. The straight line is x plus t times y minus x. This is a parameterization for t between 0 and 1 of the straight line. Calculate the length of that curve is giving you just the Euclidean distance x minus y in the Euclidean distance. This is what the Euclidean calculus does. But now we are in SL3. We are on the surface of the Earth, and we want to calculate distances on this group. How should we do this? Well, now we should use a little bit of differential geometry. We should, or we can, endow SL3 with a manifold structure. That is, on the surface, I try now to imagine this, on each point on the surface you attach a tangent plane, and in that tangent plane you calculate as if you were Euclidean, only your tangent planes are moving. And then you ask yourself, I have a measure of length in each tangent plane. I want to know the shortest distance on the sphere. That's what you are doing. For the surface of the Earth, the shortest curves connecting 2 points are the geodesics, the big lines on the sphere. And you can calculate them not by just knowing these are the curves, but you could say that, well, let's take any other curve on the sphere and try to minimize over all possible curves. And the minimizer over all possible curves which start at x and end at y, this minimizer you call the geodesic curve connecting them. And then you calculate the length of this geodesic curve, and this will give you a distance on SL3. That's what I did by endowing SL3 with a Riemannian manifold structure. I will give the precise in a moment. Then I calculated the geodesics. Then I calculated the length of the geodesics. And that gives you, a priori, if everything is right, a distance measure on SL3, which respects the group structure of SL3. That is, I am replacing the Euclidean distance, let's make here a Euclidean distance of x and y, which is defined by x minus y, the Frobenius norm of it. I am replacing this by the distance of on SL3 in a geodesic sense of x and y. The problem is the calculation of this guy. I mean, I have not yet explained to you what is the measure on each tangent space of SL3. I have not explained to you how the geodesics look like. Usually you have to solve a second order equation for finding the shortest way. And when you have found it, you have to calculate the length of that shortest curve. And then for each x and y on your group, you have to find this curve. And I can tell you, to my knowledge, no one knows the precise expression of that guy on SL3 or GL3, the general linear group, or whatever. On SO3, if you are just saying that you want to compare only rotations, yeah, one rotation to another, there is a closed form solution, and the solution is like that. I have to erase the blackboard. No way. And the result which I will give you for the orthogonal case, that is x and y are orthogonal matrices, and you want to compute the geodesic distance on SO3. Then the logarithm appears. The matrix logarithm appears. Okay, so the distance squared on SO3. Again, the measure on the tangent space, I have not yet written it down, but all these objects which I'm writing down now are following from the same approach. So I'm just restricting what I do for the other one to do the same on SO3. It's not that I'm comparing apples with peaches. So the distance of Q1 and Q2. Two rotations. Now you want to parameterize a curve in the space of rotations, starting at Q1, ending at Q2, and calculating the distance. This distance is given by the Frobenius norm, crazy, but of a completely different expression, namely the logarithm, the matrix logarithm of Q1 transposed Q2. If you see this expression, you realize immediately that to first order, the Euclidean distance is recovered. Because you can expand the logarithm, it's a series. The logarithm is the log of q of any object is q minus 1 plus the first term. So I'm replacing this guy here to first order. I'm getting not the logarithm, but q1 transpose q2 minus the identity squared. And this is just because of unitary invariance of the Euclidean norm. This is just the same as q2 minus q1 squared in the Frobenius norm, which is nothing else than the Euclidean distance is equal to the Euclidean distance. So to first order, these two distances coincide, which is of course only a consistency check. Nothing happens if you are in a neighborhood of each other. But for the bigger distance, there is a marked difference. There appears this matrix logarithm. Now back to our SL3 case. This is only possible because SO3, the group of all rotations, is a compact group. It's a compact group. It's like a circle. And this implies that you have some nice calculations which allow you to really calculate this distance and to give it a definite expression. This you can calculate. The same is not possible in closed form for SL3. Okay, we have to accept this. The question is, what use then if we cannot calculate this distance, and all our endeavor so far, if we cannot calculate the distance, it's a nice theoretical concept without any consequences. What I have shown is that the object which I am interested in, distances of some arguments to some other arguments, my object, I can calculate it. What is my object? Remember that I didn't want to calculate really the Euclidean distance of two arguments. I wanted to calculate the distance of an argument to SO3. I wanted to calculate the distance to all rotations and the minimal distance to all rotations. Yeah? I'm not calculating x to y, but x to all rotations. So what I want to calculate is, in the Euclidean case, the distance Euclidean of one object, let it be f or x, it doesn't matter, of x to SO3. And that gave us our strain measure. That was a strain measure, x, the gradient of phi. And we had been able to calculate this. This was equivalent to the square root of x transposed x minus the identity squared. So I'm not interested now for my group distance on SL3 to compute x and y distances, but to compute the replacement of this. The replacement is, I know that there is a geodesic distance. I'm not able to compute the distance of x and y, but I want to compute x to SO3. This is what I want to compute. And that took me 5 years. It took me 5 years to prove what I saw immediately. But seeing is not proving it. The result is the following. This is the same as, it is the minimum over all Q in SO3 with respect to the distance of SL3 of x to Q, like before. Still, you would say that you cannot compute individual distances. How shall you dare to think you can minimize the guy? But somehow the minimization is helping you. The result is the following. And I saw this very, very clearly 5 years ago. The result is the following. The minimum over the distances of geodesic distances on SL3 of x to Q over Q in SO3 is the same as another minimum, the minimum over all Q in SO3 over the matrix logarithm of Q transposed X, Frobenius norm. This I knew 5 years before, and the calculations and so on, I'm not going into details. It comes into play that by a result which is due to Alexander Mielke from the Weierstrass Institute, he had, in a way, solved the geodesic equation on SL3, but not in closed form, just saying that the parameterization is in principle like that, and for making it more precise you would need to solve a nonlinear equation. And I could just work with this formal parameterization, not making it precise. I cannot calculate the precise distance between two objects, but in this calculation it turned out that I'm able to show this equivalence. Which again, doesn't tell you much, because now you have just transferred the problem. This is now your distance SL3 of x to to SO3. So, and this summer I asked Nick Hyam from Manchester, who is a matrix analyst, whether he knows the solution of the minimization problem. He didn't know, but he referred me to one of his co-workers. And together we solved the problem. The answer is, to make a long story short, the Q is again the unitary factor of the polar decomposition of X. You can take X, you can write X as being R times U. You could also write here all the way down X is F. F is the deformation gradient. You take X equals R times U. The optimal Q, this here, is equal to the logarithm of R transposed X, which is nothing else but the logarithm of U, which is nothing but the Hencky strain measure, which is the square of the Hencky strain measure. Hencky strain. Okay, what I knew 5 years before, when I was writing down this here, I wanted to solve it immediately, of course, and I used the series expansion of the logarithm. And to do differential calculus, you optimize on SO3, means you have to be careful with the tangent space of SO3, some skew-symmetric matrices, getting some equilibrium equations, trying to solve them and see it. And what I saw is that as long as my series expansion works, the only critical point of the corresponding minimum principle, stationarity principle, is that Q which makes Q transposed X symmetric, which is more or less up to reflections the polar factor. But that doesn't constitute a proof, because I don't know whether my minimizer is in the neighborhood of the identity or such that I can apply the series definition of the logarithm. So we wrote a paper which is submitted, which treats the whole problem from a completely different standpoint, namely to look at a matrix minimization problem, namely this one, over any SON, not 3 dimensions, n dimensions, of expressions of this type. And we solved the problem. Namely, together with Yuji Nakatsukasa from Manchester and Andreas Fischle from Essen and myself, we proved that the minimum over all Q in SO3, the general case, the n-dimensional case, is more complicated, of the logarithm of Q transposed X for any invertible Q, for any invertible X, is given by the logarithm of the square root of X transposed X. This is submitted to Science Journal on Matrix Analysis and Applications. And I will only say a little bit about this tangent measure, what kind of metric I'm using on the tangent space. Apart from that, the story is closed. On SL3, I define a Riemannian manifold structure. I consider geodesics. I calculate distances. I'm not able to calculate individual distances, but I'm able to calculate the distance of one object to the compact group of orthogonal matrices, and that distance is given by this expression, which again is a strain measure. This is just the point. Because if the distance is 0, it must be a rotation, and then you remember the curl equation from the beginning, it is a rigid rotation. And in my opinion, respecting the group structure is really the new information here. There is no reason why you should think that you can just combine linearly two deformations. You see, deformations, you can combine it multiplicatively. You can phi 1 applied to phi 2 and so on. Yeah? And on the gradient level, that will give you a multiplication of the deformation gradients. So you have a group structure behind it, and you should, I think, respect it, and that will lead you in a natural way to this geodesic distance measure. We are very confident that we can prove it also for the n-dimensional case, and from a point of application to mechanics, the story is closed. In doing so, in proving this, we had to write another paper where we solved some finite dimensional optimization problem, which is a very strange algebraic estimate, namely the following estimate, just for the fun of it. Positive numbers, x1, x2, x3, positive, y1, y2, y3, satisfying the following estimates. x1 squared, x2 squared, x3 squared is bigger than y1 squared, y2 squared, y3 squared. 1 over x1 squared plus 1 over x2 squared plus 1 over x3 squared is bigger than 1 over y1 squared, 1 over y2 squared, 1 over y3 squared, and x1, x2, x3 equals to y1, y2, y3. This is the assumption on x and y, and everything here implies, which is really unexpected, this implies that the logarithm of x1 is positive squared plus the logarithm of x2 squared plus the logarithm of x3 squared is bigger than the logarithm of y1 squared, the logarithm of y2 squared, the logarithm of y3 squared. And this seems also to be true in any dimensions, but you have to fill up more conditions of that sort. And this is another paper which I did together with Mircea Birsan from Essen and Johannes Langkeit from Essen and Neff, and which is submitted. And we use this result to prove the logarithm result.
I have only a technical question. Your Riemannian submanifold, SL3 or SO3, have the induced Riemannian structure starting from the embedded manifold of matrices?
I will answer it by showing you which kind of metric I'm using. In a way, yes. So it's not a weird construction. It's not something which you fancy. It's just what you should do, I think. So let me check my paper, okay? So when when introducing this geodesic stuff. Okay, so I have Riemannian manifold. The Riemannian manifold is SL3, but let me write M for Riemannian manifold. M, and I need to define a metric G, a metric, which is a in each space point, x is an element of M. In each x, you have a metric, and this metric is a mapping, a bilinear mapping of the tangent space at x of M cross to R, bilinear, I mean quadratic, bilinear non-degenerate, degenerate. I will define it in a moment in precise form. And when I have such a metric, I can define the length of curves. So this is a curve gamma of S living on M. It's starting here and it's ending here, and I want to have the length of the curve. I have tangent vectors gamma prime of S. And as in classical manifold differential geometry, you need to measure the length of the tangents and to sum it up. So the length of a curve L of gamma, the length of gamma, starting at gamma of A, ending at gamma of B, is defined as the integral of A to B, the square root of measuring the length of gamma prime S, gamma prime of S, ds, and of course you have to take the metric which lives where you measure. This is at gamma of t. Okay. Now I give you G, which gamma of S, yes, gamma of S. So G must be positive definite, yeah? Let me erase the blackboard. Okay, I define the following even family of metrics in the following way, namely Gx xi are tangent, xi will be tangent vectors, x is the point on the manifold. I define this to be mu times the symmetric part of x to the minus 1 xi plus mu c times the skew of x to the minus 1 xi. All the time the Frobenius norm, and this is happening on the tangent space. That means if you consider what we evaluate there, okay, mu and mu c must be positive. And this is a metric, of course, for SL3. There is no trace term because in S has something to do with the determinant. Determinant is 1. That alone wouldn't be a metric. You control the symmetric part, the skew symmetric part, but the trace part could be missing. But for SL3 this is enough. This is a metric on SL3. And to observe what's happening here, look at this expression. So G gamma of gamma prime will be something, now I'm simplifying it, mu c equals 1, which is allowed. Then you have just to compute gamma to the minus 1 of S times gamma of S. And this guy here is living in the tangent space of the identity to the group. This one is living in T1 SL3 or T1 M. Yes, this is in our case of SL3 we have the tangent space to the identity of SL3, which is nothing else but all traceless matrices. All traceless matrices, and they are called small SL3 traceless matrices. And on traceless matrices, of course, this is anyway a norm, but also here on traceless matrices, if you control the symmetric part and the skew-symmetric part, everything is controlled. That is with the metric. I'm using the Euclidean metric on the Lie algebra. I'm getting back my tangent vectors by multiplying them with x to the minus 1 into the Lie algebra. I'm measuring them there, and that's what I do. And the result is now interesting. You see here a family of metrics. Now you could think that you also have a family of distance measures, namely to each metric corresponds a distance measure. I should label it mu, mu c, according to which metric locally I use. Good news, or surprising news, whatever you think, it doesn't depend on mu or mu c. I mean, there is a factor, but the optimum is always the polar factor, regardless of mu and mu c. Yeah, that is the story. So this is a very strong result, I think a very generic result. Yeah, it's not this simple structure here, it is not this, but in the proof we needed this family because we based our proof basically only on that guy for the minimization. Yeah, so that closes the picture. Irrespective of the family of metrics which you use in this family, you always get the optimal rotation, the unitary polar factor. Thank you.